Hello, welcome back to Educator.com and welcome back to physical chemistry. So we finished our discussion of quantum mechanics, and when we did thermodynamics, at the end of that portion, I had a lesson where all of the equations were put in one place. I decided to do the same thing for quantum mechanics. So that's what this lesson is. It's basically going to be a quick review of quantum mechanics, just talking about what equations we actually dealt with and what are the important things. We saw a lot of mathematics. This lesson distills all of that into what is essential. Okay. So we had the de Broglie relation. So basically it is the wavelength of a particular particle of mass m traveling at a certain velocity v. If you take Planck's constant and divide by the mv, you're going to get the actual wavelength of that particle, treating the particle as a wave. We had these statistical relations. It's what we talked about in the beginning. So if you have a bunch of values, the average value of x is going to be the integral, this negative infinity to infinity is just over the particular space that you happen to be dealing with, of x times p of x dx. This average value of x squared equals this, and this variance, which is this sigma squared, is the one thing minus the other thing squared. That's always going to be greater than or equal to 0, and p of x is the probability density. P of x dx is the probability. And we'll see what probability density and probability are for the wave function in just a moment. And again, these are just reminders of what it is that we did. We had the Schrödinger equation. This is the equation that we set up for any particular quantum mechanical system that we're interested in. Depending on what this potential energy is, we set up the equation, we solve the equation, and we get a wave function, psi. From that wave function, we apply different operators to that wave function to extract information. That's all we're really doing in quantum mechanics. We set up a Schrödinger equation, we solve the Schrödinger equation, so we get the actual psi, the wave functions, and we get the energies for each one of those wave functions, and then we do things with that wave function depending on what we want to extract, what sort of information. The solution, psi of x, describes a particle of mass m moving in a potential field, v of x. The Schrödinger equation expressed as an eigenvalue problem. The Hamiltonian operator applied to the wave function psi is going to equal some scalar e times psi, where h is the Hamiltonian operator. This is the Hamiltonian operator in one dimension. This is the Hamiltonian operator in 2 dimensions. This is the Hamiltonian operator in 3 dimensions. These are partial derivatives. The particle in a one-dimensional box. This was the first quantum mechanical system that we discussed. The psi, the wave equations for this, ended up being, so a particle of a one-dimensional box of length a. Particle moving back and forth. Where is it? How fast is it going? This describes it. The energy is this. The wave function is this. N is the quantum number. Takes on values 1, 2, 3, 4, 5, 6, 7. So it could be in the C1 state, C2 state, C3 state, C4 state. It could be in a bunch of quantum states. That's the whole idea. The particle in a 2-dimensional box of area A times B, A by B. 2-dimensional box, just 2 dimensions. This is the equation for the wave function. Now, x goes from 0 to a, y goes from 0 to b. You have 2 quantum numbers, n sub x and n sub y. The energy is equal to this. The n's, they vary independently. You don't have to have 1, 1, 2, 2, 3, 3. It could be 5, 14, 3, 8. They vary independently, the quantum numbers. The particle in a 3-dimensional box. You're just multiplying the individual equations for a 1-dimensional box. So it's this whole thing. Note a function of 3 variables. X goes from 0 to a, y goes from 0 to b, z goes from 0 to c. Now you have 3 quantum numbers. They vary independently. This is the expression for the energy of a particle in a 3-dimensional box.